that because it's difficult, as I said to you on Monday, to talk about this stuff. It's very delicate in terms of some of the subscripts and things. And I found one typo in the notes I gave you the other day on page 8. We'll talk about that later. Anyway, so what example 1 does is it sort of does the problem, and then the author goes through a procedure to solve such problems, but he doesn't do it the same way. So we've already gone through that procedure. I think if we now go back and stumble our way through and then go back to that procedure, then a lot more stuff will make sense. I'm hoping that that's the case in any event. So I've got some things written down later that will allow us each time we do it to solve it. But at the beginning, we're going to assume that we don't really understand much about this, except that we know P of x in this particular case, capital P of x is 2x squared, capital Q of x is minus x, and capital R of x. This is the case every time. And then what we do, as you know, is we divide supposedly. So if we did that, the little p of x will be in this particular case minus x over 2x squared, which will simplify to minus 1 over 2x. The q of x will be 1 plus x over 2x squared. And that's kind of what we've done in the past. If we were believing that we had a regular solution, like if we wanted to solve this problem at x equal 1, then that would, 1 is an ordinary point. I said regular a second ago, ordinary point, and therefore you just do a power series around 1. So you'd have x minus 1 powers, and you stick that into the y double and the y prime and so on, and solve it like we've done in the past. However, in this case, as you notice, if I let x be 0, the second derivative wipes out. And basically that says that we don't have an ordinary point, or at least we have to look into it. You look into it, and that involves what these two things are. And what we found out is we can solve this problem if x p of x and x squared q of x are analytic. In this particular case, the x p of x is minus a half, and the x squared q of x is 1/2 plus 1/2 x. Now, I wrote that out for other reasons, but it's 1/2 times 1 plus x. Those
Dr.
are
Brady.
both analytic functions. Both of them are polynomials, and therefore we go back to the theory. The theory basically says if these two, if x p of x is analytic, which it is, and if x squared q of x is analytic, which it is, then we have a way that we're going to solve the problem.
Dr. Brady,
Yes.
someone needs to be let in.
No, yes. One more person. Okay. So, Emma, sorry I didn't see you for a minute. In fact, I didn't see you at all because I wasn't looking. Anyway, so we've checked out stuff here. We have 0 is an regular singular point. Now, what we're going to do is write out this right here. This is going to be P naught plus the series from 1 to infinity of pk x to the k, because these are power series. Now, these are simple ones in this particular case. This is going to be the series q naught plus the sum. I like to write out the q naught and the p naught, as you know. And that will be q sub k, x to the k. In this particular case, we can identify p naught is minus a half, and pk is 0 for all k greater than or equal to 1. So we only have one thing here because this whole series collapses just down to one number. And the Q naught is a half, Q1 is a half, and all the other Q's are 0. And that's going to turn out, when we get the general method, right now it doesn't mean much. When we get the general method of solution, that will mean a lot to us. But we identified basically the coefficients of the power series. And in this particular case, we don't have very big power series. We just have a couple of numbers and an X. But anyway, now the book also suggests, because I'm reviewing as well as doing this, that we write the problem maybe in the following form, and that's x squared and then whatever else we have. And the book says we do this xp of x, y prime, and x squared q of x, y, except, so that's what we want to do, but in this particular case, what would that mean? Well, if I take the original thing and just divide by 2, what I will get, but if I use this particular thing here, if I just divide by 2, I will have minus x over 2 here, and over here, I will have 1 plus x over 2. And the point is that the book wants us to write it like what I just erased, okay? And so if I do that in this problem, I will get the following. I'm leaving some space that I don't need in this case. And I will get 1/2 plus 1/2. Now, the point is, when you look at it, this is, you want to write this so you have the power series of P right here and the power series of Q, I beg your pardon, the power series of XP here and the power series of X squared Q here. And if you'll notice, all I did was rearrange things a little bit, but this is a whole power series. It breaks down to just a half. This whole power series here breaks down to just that. So in this, so if I'm just working this thing out without knowing all that stuff I wrote to you on paper the other day, and without knowing what the author is going to do next, we wouldn't do all this stuff, okay? What we would do is say, okay, I'm going to assume that I have a solution of the following kind. In other words, we wouldn't know to play around with all this stuff. Once we've gotten that xp of x is analytic and x squared q of x is analytic, okay? And there's other ways besides what I just did to find P naught and Q naught. We'll talk about that. We did the other day. We'll talk some more about that. We're going to assume the solution looks like the following thing. X to the R times, like right now, a sub k, x to the k. So we're just going to assume this, as I say, without all this other stuff. And if we do that, then the derivative, as you can tell here, first, it's not so convenient to write it this way. When I write it this way, I've got to do a product rule, so I don't want to do that. So I'm going to write this from 0 to infinity, a sub k, x to the k plus r. Now, I told you the other day, I like to use k's instead of n's. One of the reasons I do is I find that when I do n's, my n's and my r's, when I'm writing fast, look alike to me. In other words, when I write fast, this begins to look like n's. And so I make mistakes when I use n. If I use k instead of n, I'm not so likely to make mistakes of distinct. In other words, k looks enough different from r that when I write stuff on a page, I don't make the mistake of confusing n with r. Now, if you write as badly as I do, I suggest that to you. If you write nicely, how you write can be put into postcard to wedding announcements and stuff, that's great. You don't have to do that, but I do. Anyway, y prime. Now, I have k plus r power. This is a polynomial, you know, if I wrote it out a little bit, it would be a naught x to the r plus a1 x to the r plus 1 and so on. So when I differentiate, you're going to still get the same power series index from 0 to infinity. We do it term by term. So I'm going to have a sub k, k plus r, and x to the k plus r minus 1. When I do the second derivative, I don't want to do these too many times because it just takes too much time to do this, and this you guys can understand, no problem. But when I do another derivative, it's going to be k plus r minus 2, x to the r plus k, or k plus r minus 2. Sorry, minus 1, and then that. Okay. Now, these three things I've got to stick into the original equation. So I suggest, and of course, with my space here, you guys realize with the space here, I have a problem. So what I'm going to do is multiply this one. So those of you who see the video, it'll look okay, but if people just walk in a couple of minutes here, not going to be okay. But I need to do 2x squared here times y double. In other words, this equation is going to end up with 0, but so I'm going to multiply here by 2x squared, just so I don't have to rewrite everything, and that's going to raise the power here, which is a minus 2 to back to r plus k. I'm going to take the minus x and multiply it times y prime, and that's going to put a minus here maybe on the ak, and over here this is going to be x to the r plus k. And then this one's a little more trouble because I got to multiply by 1 plus x in this problem. So I got to write that down. 1 plus x times the series, k equals 0 to infinity, a sub k x to the r plus k. That's actually going to be two series, which I make into one series in a minute. That's going to be this repeated thing, 0 to infinity, x to the k, x to the r plus k power, plus sum from 0 to infinity, a sub k, x to the r plus k plus 1. Now, I want to add the three things I changed here together to get 0. But here, all the powers are x plus or plus k plus r, except this one. So this one I'm going to change. I'm going to change by decreasing the meaning of the index down 1, which will increase the meaning of the index here up 1. And so these are things that you have to do. You've got to do these problems yourself or you'll never understand this. This is going to change to k plus 1. So I'm going to have a k from 0 to infinity. So I'm going to split off the 0 one. Now a 0 one is going to be a sub 0 x to the r. And then this is going to be the sum from 1 to infinity, a sub k x to the r plus k over here. And this one is also 1 to infinity, but when I decrease the meaning of the index, this is going to be a sub k minus 1. So to put these two together, I'm going to take the first term with the 0 off of the beginning, and that leaves me from 1 to infinity of this same thing. Then I'm going to decrease the meaning of this index by 1, which changes this to 1 to infinity, and then I can add them. So it's this thing I want to add to these other two things, okay? And that's kind of a mess at the beginning, but I think it's important for you to see. Now, over here, I think I can erase some stuff down here that we'll go back and talk about a little bit. Let's see what we get. And as I said, you guys need to do this yourselves, but I will get the series from 0 to infinity, 0 to infinity, and this is 1 to infinity. So I better take off the first one here. So if I do that, when k is 0 for the 2x squared y double, if k is 0, that's 2 times a sub 0 r and r minus 1. That is times x to the r. So when k is 0, I just wrote down what this becomes, and I'm going to have a plus the sum from 1 to infinity of all that stuff, 2a sub k, k plus r minus 1, x to the r plus k, but that's going to be way over here because I'm going to put other stuff together. So that takes care of this first thing, which is the 2x squared y double. I've got to add this to it. This is also 0 to infinity, so I'm going to steal out the 0 one, put it over here. The 0 one is going to be minus a sub 0 r, x to the r. That's this one. And then I'm going to have the rest of this stuff is going to be minus a k plus r, because I've got 1 to infinity, and that's where I'm putting this stuff. And then I got this thing down here, and I have an a naught x to the r. That's this one. Then I have from 1 to infinity, so I can just copy this stuff, and that's plus a sub k plus a sub k minus 1, I guess. Anyway, this stuff you have to be real careful about. I don't know if I'm being careful enough because I'm not thinking right now. I'm just writing. When you're doing this on paper, you carefully make sure you keep all the subscripts and superscripts and all that kind of stuff together. But I'm trying to get to what the book has on page 221. So trying to show you how you get there, okay? Now, so, and what was this thing here? This was, thing I think was here, that was minus a sub 0. So, okay. Now, all right, in this term here, what I noticed, if I didn't make any mistakes, is I have an a naught in every one, and I have an x to the r power in every one. So if I take the a naught out and the x to the r power and see what I have left, I have here 2r times r minus 1 minus a naught r, I'll give myself a little more space, minus a naught r plus 1 x to the r. Okay? Now, here's a place where things will differ from the general case. We're going to, maybe I can put it up here. We're going to be talking about something called f of r, which is r times r minus 1 plus p naught r plus q naught. Now, what I just have gotten is 2r times r minus 1 minus a naught r, shouldn't be minus a naught, should just be minus r plus 1. Okay, now, the reason when you do this later, because later we won't do the problem this way necessarily. We could do it this way, but we have another way to do it that we need to, we'll talk about. Okay, so the point is that I have r times r minus 1. Here I have 2 times r minus 1. But remember, in this particular problem, we started with a 2 here. Okay, and what the book does in general is gets rid of this 2 if it's there. And if you got rid of the 2, that would make an x over 2 here and a 1 plus x over 2 here. Here's the 2 in the denominator when we do this more generally. And so if I divide it by 2 here, because remember, I'm going to set this equal to 0. If I divide it by 2 here, then let me go ahead and say, this is the thing which is going to be set equal to 0. That means every coefficient is 0. And although I don't know it yet, if I set this equal to 0, that's 2r times r plus 1 minus r plus 1 set equal to 0. Now, what is this thing here, which again we will be using later? That's r times r minus 1, p naught. What's p naught? P naught is minus a half. And so that would be minus a half r. Here it's minus r, but it's 2 times out here. If I would divide this equation by 2, I would get r, it should be r minus 1, minus a half r plus a half. And if you look up here, the p naught's minus a half and the q naught is a half. And so even though I don't realize when I'm doing this the blue collar way, this thing I get is twice f of r, and we're going to assume f of r is 0, so twice f of r is 0. So the point is that doing it this way, which is the blue collar way, and doing it later another way gives us this thing coefficient of the r power. Okay, that's sometimes hard for people to see, so I'm hoping you're going to understand this stuff by me doing what I did Wednesday or Monday first. Now we do the example, and then we'll go back to what I did Monday. Okay, anyway, this is going to be equal to 0, and it has to be, and notice this rest of this thing is a complicated deal, and that's also going to be equal to 0. Okay, now there's something else about this complicated deal, although I don't know if it's written enough yet to see it, but here we have k plus r and k plus r minus 1. If you look at this roughly, not 100%, because we haven't played with this yet, but if you look at this roughly, and you look at this roughly here, this one here, and this thing here, right now they both have 2. This has an a naught, this has an ak, and so on, but we have k plus r minus 1. Here we have r and r minus 1. The point is, this is going to turn out to involve f of k plus r instead of f of r. So this thing, which is complicated, is also going to involve f later. Right now, I haven't written out enough of it for you to see that it's the same thing, because partly my space and partly time, but this thing simplifies down to using f of k plus r if I've identified what f of r is. Okay, so now, again, everybody's home except one person here today, so I assume you have your books. What we do is, since this equation has to be 0, we solve it. Now, my problem, of course, is I don't have any space to solve it for you guys, and so I'm going to get rid of some of this, and I may be sorry for doing that in a little bit, because I might need something like that. But if I try to solve 2 times r, it's going to be r squared, 2r squared minus 2r minus r plus 1 equals 0. That's 2r squared minus 3r plus 1. That I can factor to 2r minus 1 times r minus 1, I think. I'm just doing that quickly. That's 2r squared minus 3r. Yes. So I get 2 roots, a half and 1, from this equation, which we are later going to call the indicial equation. These 2 roots tell me what my solutions are going to look like. Now, because of what we did Monday, and hopefully you didn't forget everything we did Monday, we said we get 2 numbers. The numbers are either real and different, or equal or complex. 3 cases. Actually, there are 4 cases, because we don't want, as you'll find out here when we get back to the more general case, we have to make a 4th case when the difference of these 2 numbers is an integer. Now, we're going to get 2 solutions. We're going to get a y1 solution, and we're going to go to y2 solution. The y1 solution is going to be based on the biggest of these 2 numbers if they're real, And so R1 here is going to be 1, and R2 in this problem is going to be a half. Do we always take the biggest one is R1? And to indicate that, the answer here is going to be A naught of R1. We're going to write that. The answer here is going to be A naught of R2. We attach the R1 and R2 here so you know which one of these things we're dealing with. Okay? And it's going to be a power series, and it's going to be AK R1 x to the R plus K. I'm running out of space here. And this one's going to be the series from K from 1 to infinity. And it's going to be A sub K of R2 x to the R plus K. Now, what I just wrote is actually wrong because I'm just trying to write it out. This is going to have x to the R on it because remember all these solutions, and I erased it, all the solutions are x to the R power outside. So let me rewrite that. I'll just do y1 here. Y1 of x is going to be A sub 0 of R1 x to the R plus and so on. Now, before I go further, when you go back here and look at this problem, and this is an important point that is hard for people just to kind of see immediately. The book says something, but it doesn't say it very well. This is got to be 0. That's where we got the 2 R's. So this thing has to be 0. What does this thing have to be? The A naught times 0 is what we're going to have. So the point is, it doesn't matter what the A naught is. Any number you pick for A naught will make a solution. So, because again, what you have is A naught and you have F of R, we're going to find out, and that has to be 0. And so if this is 0, that means this can be anything else. Therefore, we always choose A naught to be 1. And so this thing here that I did is always going to be x to the R times 1 plus the series K from 1 to infinity, A sub K of R x to the K. This is just a power series, but it starts with 1 every time. And we put the R. Now, this is Y1 is going to be R1. And so it's going to be R1 here. Now, depending on what case we have, the Y2 is not necessarily, doesn't necessarily look this way. In this case, when you have the two roots are real and the difference does not equal an integer, in this problem, in this example, Y2 is going to be x to the R2 of 1 plus the sum from 1 to infinity, A sub K of R2 x to the K. So the two solutions are going to look alike, except one's going to be x to the 1 and the other is going to be x to the 1/2 out in front of these. Okay, having said all that, this is what the solutions look like. What do we not know? We don't yet know what the coefficients are. Okay, well, how do we find the coefficients? We have to set this thing equal to 0. We have to set this thing equal to 0 and start solving for coefficients, because this series from 1 is going to involve A sub K here, and that's A sub 1. And so we have an equation here that involves A sub 1. And if you look over here when K is 1, we got an A sub 0 in here. We've just figured out that A sub 0 is always 1. Okay. And so anyway, we're going to be able to get A sub 1 in terms of A sub 0. Then we're going to get A sub 2 in terms of A sub 1 and A sub 3 in terms of A sub 2. And so we use this equation, which is complicated, to figure out what all the coefficients are. And this is what the book does on page 222. he gets a general solution at the bottom. So now, just from our time standpoint, let me assume that we went ahead and solved this equation, set it equal to 0. When you do that, in this problem, you get a sub n, now I use k, is a sub k minus 1 over 2 times r plus k squared minus 2 r plus k, sorry, minus 3 r plus k plus 1. So when you solve this one for 0 and divide and find ak, this is what you'll get. I highly recommend you do that, not from my statement. I'm not even sure this is right, because I kind of screwed it up right over there. But basically, when I wrote it, it was right. It's just, when I look back at it, I don't know what that is. Okay, so you guys need to do this. But this is what we get for what I write, k greater than or equal to 1, the authorized n greater than or equal to 1. Same thing, except as I already explained to you. See, look here, when I do this, I stick the thing through the k. If that was n, it would look like r, and that's why I do it. Okay, one of my frailties. When I look back at the notes I took in college, they were beautiful. But my fingers just don't do that anymore. Okay, so this is what you get. So we can figure A1, we can figure A2, A3, it's a recursive formula, and we get all the things and we write down the answer. That's what the book does. Notice that when you read page 222, it takes the whole page to do that. So finding these things is not necessarily just 2 lines. It takes him half or 3/4 of the page to do that, and he gets the 2 solutions. And that's the example. Okay. Now, so having said all of that, I now want to, and I've got to share the screen, except I didn't go yet and get what I'm going to do is go into Blackboard here. I'm sorry, I did not do that ahead of time. Come on, Blackboard. So you guys can't see what I'm doing, I guess. Doesn't matter. Getting into Blackboard and getting to the material I've sent to you guys, which is in course materials. So I'm trying to find that now, going down to it. Chapter 5, section 5. Hello, machine. Okay, I've got it here. So what I now need to do is share the screen. If I can find Zoom again. No, that's not it. Where did my Zoom go? I'm still up. It's amazing. So let me try to do it over here. There's a co-host. I don't know if this will work or not. No, it doesn't work. So I can't share that way. It's interesting, in 2 screens, and one of them's got my face or my shoulders and stuff in it, and one of them is gone. So where did it go? Let's see here if I can get it back. I'm sorry, this stuff is crazy. I don't want to share the screen. Stop the share. Boy, it's maddening when this stuff happens between the 2 computers. So I can go back in. I do not get back. There we no. Sorry. It's got me. Okay, how do hello? I can see myself as a little picture, but I don't know how I get back. sorry for this stop. I'm stuck because I don't know. I know if I hit the right thing, it'll give it back to me, but what it wants to do is enter the meeting again. And of course, I've got my body right in front of you, so it's here. I just can't get that on my screen here. So how? Hope you're patient and put this in the teacher evaluations that the instructor can't ever do anything. I don't know how to get back. Got a little picture of myself. Stop the video, remove the pin. Stop the video. Mute my audio, don't want to do that. I can't. As I said, I've got Blackboard up here, and I've got a little picture of me on the screen and a big picture in the other computer. But I don't know how to get this back. SB, settings, change my picture, help, switch accounts, sign out. Okay. Just a second here. No idea. Now it wants me to sign back in, but I'm in. This is crazy. Anybody know how you can get back? I have no idea. I can go back through the whole process, but I'm already in there. I'm talking to you if you can still hear me. So it's crazy. Wants me to get back in, but I'm in. I do not understand what happened here. So come on, machine. Because it won't go back to, I've never had this happen before. So come on, machine. I think I just got back. Yeah, but now I've got a double screen here. Let me, I think I'm back. Okay, that was a wonderful trip. All right, maybe. No. Now, where is, okay, now I got rid of Blackboard. Just a moment. Go to Blackboard again. You guys are being very quiet and patient. I don't understand that. You're usually rambunctious and rude and mean and everything.
It's still early in the morning.
Thank you. Anyway, okay, get back to course materials. Get back to the screen, and I don't want to lose myself now, as I did before. I have no idea why it canceled there. All right. So now if I share the screen, finally, now you should see a share screen. Yes. Okay. So I need to make it bigger. And now it still wants me to sign in again. Okay, just a second. You should be seeing the screen getting bigger and stuff. Sorry, this is what I try to set up before class, but so if any of you had to take a lunch break or bathroom break, now you can come back. Okay, finally, maybe. I don't know why it's not further bigger. Okay, I'll have to put up with it the way it is here. Wasted enough time. Okay, to redo what we did the other day in the pages I handed out to you. That stuff started, as you know, with things at infinity. So it wasn't until you get to the bottom of page 2, where we start doing what I did at the very beginning of today, and I'm not going to repeat that. That's all the same stuff that was written on the board at the beginning. And we also assume we define this f of r thing, and we name it and all that. You know all that. So we're going to solve the problem differently now. This is not the same example. This is a general problem. And so we're going to assume the solutions look like this, just like we did when I wrote it out a while ago. And when you differentiate twice, again, I did this on the board for you today earlier. I called this y instead of phi, but that's the same thing. And so we go do that. We stick stuff into the equation. When you do that, remember we had x squared because, let me go back here. We write the thing like this. It's the second line on page 3. I write the equation like this. So I have an x squared out in front of the y double. I have an x out in front of the power series p, and I have the q power series out there. And so now I'm going to go down and show you that here. Here's the x squared. Here's the x. Now, big danger warning and stuff. People sometimes mess this up because they forget this x right here. Anyway, when is x squared times stuff? This is the second derivative of the y, or the phi. This is the x, p of x, and this is the first derivative of the y. And then we have the q. This is actually x squared q of x, and we have the y. So we have to combine that stuff. I want to get to some other things here, but you combine the stuff, takes a line, and we put stuff together. That's where I try to make everything the same power. I did all this today, earlier for you. Then do a little hiatus here in the notes because we have to write down these two in general. Now, in the example I did, remember that Q naught was minus a half, or the Q1 was a half, and the P naught was a half, and we didn't have a whole power series. In general, the P and the Q are whole power series, so we have an infinite number of things here to multiply. You may remember I multiplied 1 plus x in the example. That's because that was the only part of the power series we had. We didn't have 1 plus x squared plus x cubed. We just have 1 plus x. And so it's more complicated when you have a whole power series. So we call the one thing C and the other thing D. And I wrote on pages what it is. So C is this and D is the other thing. One has to do with the P's and one has to do with the Q's. So instead of this thing, we have a D thing, okay? And we stick stuff in. When we do that, we get this more complicated thing. I'm now on page 5. And I write it out. And this will begin to look like the same thing as I wrote in the example. We split off all the A naught things, and we're left with all the 1 to infinity things. And now I'm using n instead of k because the book does, and in print, I can see the difference between r and n, and so I don't have to use k to avoid myself making mistakes, okay? And over here, the author does, and so I did. I used j instead of k. You just have to use something different from n. And in the thing we did, the example, we had some of this stuff right here. And over here, we didn't have a whole bunch of this because there weren't any. The P1 was 0, the P2 was 0, the Q1 was 0, the Q3 was 0. And so this thing here, which was the complicated thing on the board a while ago, you have this f of r, and then you have this more complicated thing. Now, this more complicated thing I write right here. So if we were going to do the problem again, the example again, what I could do is identify the Q naught, the P naught, the Q1, the P1, the Q2, the P2, and all that, and just write this equation down because it's going to be the same every time. Now, this is a little bit of a different equation to write out because when we start out with 0, we end up with Pn. When j is 2, we would have n minus 2. And so this is starting with the highest power of P and going down. When you get to n minus 1, n minus 1 is P1. So the way this series is written, is the highest coefficient of P down to the lowest coefficient of P, and the same for Q. Now, in the exercise the example we just did, remember the P1, P2, P3 were all 0. So when you substitute in here, when J is 0, you have Pn. Well, if n is anything bigger than 1, okay, when n is 1, I just get one term. I get J is 0, I just get P1 here, but P1 was 0. So in the example we just did, all of these are going to be 0. All of this stuff right here is going to be 0 in the example we did. In the Q thing, what these are is Qn, Qn minus 1, Qn minus 2. Only the Q1 is going to be different from 0. So in the example we did, this series, finite series here, breaks down to just like 1 or 2 terms. But that's what it is in general. So as I say, we could start out and identify what f of r is. And so I'm going to do that again. Once I know, I mean, I did it already, but once I identify the p, little p, and x times p and x squared times q, once I've identified that, I can figure out what p naught and q naught are. And once I do that, I know what f of r is. Once I know what f of r is, I know what the 2 roots are, and then I can build my solutions. And so now, in the notes here on page 5, we talk about what happens when x is negative. And so in the end, what we'll be doing, it's on page 6, I believe. Where's page 6? Yes. We're going to be assuming the solutions have an absolute value in them. And you can always put that in at the end. And so this is what I wrote earlier. Phi sub r is going to be really y sub 1, if you like, or y sub 2. Or if you want, you can call it phi sub a half and phi sub 1, like the 2 we have. So you can either name the answers y1 and y2, or you can name the answers using the roots. Here I use the root as the answer, phi sub 1/2, for example. And then we go into cases here showing you what these things are. A sub n, in the first case, this was the case of the example. Remember, one root was 1 and the other was a half. So this is what every coefficient is going to look like. So this is what you have to solve. So you know what f of r is, you figure f of r plus n, you know what the p's are and the q's, and this will give you all the coefficients in terms of lower ones. A50 will be in terms of A49, A48, A47, and so on. Okay? And so anyway, that's what the notes are, except, and it's 20 after. I did one more example, and we went through it quickly the other day, of a second example, where in this case, we're doing this at 1 instead of at 0. And so the p and the q, it's not x p of x, it's x minus 1 p of x, and x minus 1 squared q of x. You got to get that straight. So when we're doing it something besides 0, you have to multiply by something different. It's not x p of x, it's x minus x naught p of x. And I go through that case to show you what the solutions are, and we are out of time. And I'm sorry we lost a few minutes when I couldn't figure the thing out. Still don't know how we got off, how I could be showing up on the screen and have no program in front of me. But I'm going to stop.